Tom Zuber. I'm the managing partner of Zuber Lawler. We're a law firm headquartered in Los Angeles with offices in Chicago and New York and various locations in between. It's a pleasure to speak with you. I'm here today with Subodh Kulkarni, the president and chief executive officer of Rigetti Computing. Welcome, Subodh. It's a pleasure to speak with you. And do you want to tell us a little bit about yourself and your company before we dive into this exciting conversation?
Sure. Thank you, Tom. Excited to be here and nice to meet all of you. So I'm Subodh Kulkarni. I joined Rigetti as a CEO a couple of years ago. Before that, for almost 3 decades, I've been in the semiconductor industry in either the manufacturing process side of semiconductors or semi-cap equipment for semiconductor industries. Before that, did my PhD in semiconductors. So basically, I'm a semiconductor guy who has moved to quantum computing a couple of years ago. Rigetti Computing is at an exciting point in quantum computing. I mean, first of all, quantum computing itself is in a very, very exciting phase right now. It's going to go through an explosive growth potential in the next decade. For the last couple of decades, quantum computing was still very much in the academic research domain and proving the concepts. We are finally at a point where we are beginning to see the real value of quantum computing and what it can enable. And it's mind-blowing. I mean, the kind of problems we can solve, the computational power benefits we can get, and also energy savings we can potentially get with quantum computing is just incredibly explosive. And that excites us tremendously given where we are and what we could do in the next decade or so. So Rigetti is one of the leaders in quantum computing. We play in what we call superconducting quantum computing. That's a particular way of doing quantum computing. We, along with some other larger companies like IBM, Google, Amazon, but there's also smaller companies like us, like IQM, Quantware, and so on. A very exciting space. We are building essentially a quantum chip, if you will, in our fab, and then cooling it down at really cold temperatures like 10 millikelvin and creating the quantum effect. And that's how we are generating the computation. Rigetti has been around for about 10 years, started by Chad Rigetti, the founder. He left the company about 2 or 3 years ago. That's when I came in as a CEO. But we have continued the name and we continue the journey of improving our technology to the point where we believe we can start demonstrating real value with quantum computing in a couple of years. So right now, our focus is basically improve the technology to demonstrate practical value of quantum computing in the next 2 or 3 years.
Well, you said a couple of exciting things there, and I want to touch on them. One, the energy savings. I haven't thought about that. What do you, can you elaborate on that? That's something I haven't focused on.
Yeah, absolutely. I think people forget that. I mean, everyone gets excited about with quantum computing because of the exponential power of qubits to entangle and the computational benefits we get. And that's absolutely true. And we should never ignore that. That is one of the main reasons. But what people forget is that the same exponential power that gives us computational power benefits also helps us reduce the energy consumption. So if you think about it, a supercomputer right now has like 10 million or 20 million CMOS chips. We can do the job of 10, 20 million CMOS chips with a single quantum chip. So you consume a lot less power. And if you think about what's going on right now with GPUs, that's a big headache right now. I mean, the GPUs consume a lot of energy. And you literally are talking about small nuclear reactors next to data centers now. And that's not a sustainable equation. So I think one of the real benefits of quantum computing is energy savings as much as computational benefits.
Well, in retrospect, that seems quite obvious, doesn't it? But that really is potentially a sensational benefit of quantum computing. And we're going to get to the commercialization of quantum computers. I heard you say 2 years, and I want to explore that because that's a very exciting timeline. Let's go ahead and start with some context, though, if we can. Rigetti has been at the forefront of quantum computing innovation. Can you share your vision for the future of quantum computing and the role Rigetti plays in shaping that future, just to set a general tone for the rest of the conversation?
Sure. So first, quantum computing as a whole area. I mean, we are literally just at the infancy point here with the potential explosive growth. There are many reports that talk about the size of the quantum computing market. And in general, the numbers are in several $100 billion, roughly a decade from now. But it's never a linear line when you talk about businesses, emerging businesses like quantum computing. There's a few inflection points that drive that growth. The first inflection point we believe is in about 2 to 3 years. We call it narrow quantum advantage, which is when you can practically demonstrate practical applications and demonstrate that quantum computing is superior in performance compared to classical computing. The next inflection point we'd see is 5 to 6 years from now, which is broad quantum advantage. Basically the same thing, but with a lot more applications. And there you can start talking not only
Which is
performance.
what? Can you repeat that word? You said which is what in 4 to 6 years?
Broad quantum advantage.
Broad quantum advantage.
Yeah.
Thank
Some people just call it quantum advantage.
you. Yeah.
So that's when we can really show that quantum computing is superior than classical computing for most practical applications. And you can take problems that are kind of impossible to solve with classical computing. And that really is where the energy discussion we just had earlier. That's when you'll be able to show that quantum computing actually consumes less energy than classical computing for many, many applications. So two big inflection points, 2 to 3 years from now, narrow quantum advantage, and 5 to 6 years from now, quantum advantage. Assuming those happen, and we strongly feel they will happen, uh, then the business will indeed be several $100 billion 10, 12 years from now. So that's what the whole quantum computing industry landscape looks like. Now, within that, Rigetti, we are focused on, as I said, superconducting quantum computing, which is a subset of quantum computing. We believe superconducting is one of the leading modalities, if not the leading modality. And we'll get into that, I'm sure, on the pros and cons of different modalities.
Yes.
Um, but within that, we believe Rigetti is very well positioned compared to the competitors. I mean, and we realize we have some really big companies as competitors, including IBM and Google, and frankly, government of China is investing very heavily in the superconducting area. But we have a lot of IP in this area. We have more than 200 patents. We have been, as I said, we've been in this business for about almost a decade now. So a lot of the foundational IP belongs to Rigetti. Right now we have a 84 qubit quantum computer that is really good, that is sitting on AWS and Microsoft Azure that anyone can use. So it's a competitive race. It's an exciting competition going on between us, IBM, Google. We think we are the three leaders in this space. We
Yeah.
don't know exactly where government of China is, but we think they will be in the same league where we are. So we continue to stay focused on being a technology leader. So our goal is to continue to increase the qubit count, increase the fidelity, make the gates faster, and so on. And that's the way to get to that NQA milestone 2 to 3 years from now.
Very exciting. One of the milestones, of course, to be achieved before broad commercialization of quantum computers is scaling. Scaling quantum computers remains a major challenge. How is Rigetti addressing the technical and practical hurdles associated with increasing quantum qubit count and at the same time maintaining the coherence that makes this power possible?
Scaling is one of the areas where we probably are the most differentiated in the superconducting modality side. So if you look at what everyone else is doing, IBM, Google, and other companies, basically they're making the chip larger to increase the qubit count. So they're just going that. And for a while we were doing the same too. But about 2 or 3 years ago, we started working on a completely different approach, leveraging the chiplet approach from the CMOS industry, the conventional semiconductor industry. So instead of just making the chip larger, what we are doing now is taking a small chip, our 9 qubit chip, and perfecting it. And we are tiling the 9 qubit chips like chiplets in the semiconductor industry. And then we are using an interposer to tile those chips, and we can have the entanglement effect across the different chips. We have proven that it works just fine. So our approach in scaling the qubit count is basically tiling more and more of 9 qubits. Now we may choose a different number. Right now we are staying with 9 qubit because we feel it's a good number to scale up, but it could be a different number. It could be 36 or it could be 100 qubit or something like that. But we firmly believe that chiplet approach is the way to scale up the qubit count without sacrificing performance. And in that sense, we are different than other companies in superconducting and certainly other modalities.
So IBM, Google, these other companies are not using this idea of chips to achieve scaling of qubit count.
They are not using chiplets as of today. Now, IBM has made some statements that they are planning on doing that, but as far as we know, they haven't demonstrated chiplet approach as of today. We are the only ones who are going this route and demonstrated it so far.
Can you give us a size of the scale here? I mean, literal size. What's how big is a chiplet, and what does that look like?
So our 9 qubit chiplet right now is 6 millimeter by 6 millimeter.
Okay.
So if you do the math and say that you want, let's say, fault tolerant quantum computer that we are all looking at about 7, 8 years from now, we are talking roughly 500,000 to 1,000,000 qubits at that point. And even with the current geometry we have, which is 9 qubits in 6 millimeter by 6 millimeter, maybe a factor of 2 reduction, which is not that difficult to do in semiconductor industry in terms of the density or areal density. we can fit in roughly 500,000 to 1,000,000 qubits on a panel about a meter square. And that's so like your large panel TV, basically. And we can fit in 500,000 to 1,000,000 qubits. And that's really our vision of how we are going to get to a fault-tolerant quantum computer 7 or 8 years from now.
What does the rest of a quantum computer like that look like today, and what does it look like in 8 years? Not the 500,000 qubits. I'm talking just something with 9 qubits. What's the rest of the computer look like? In other words, when we have visions in our head of quantum computers, we picture these huge hydrogen cooling chambers, right? So what does this look like today? A 9 qubit, let's say a 9 qubit capacity, and what does the whole computer look like in 6 or 7 years?
So if you go to our website, or frankly anyone's websites, IBM or Google's too, you will see in the superconducting quantum computing something which looks like a cylinder when it's actually working. It's a dilution refrigerator with a control system sitting next to it. So control system is basically CPU, GPU servers feeding the information and taking the information from the quantum computer. The physical quantum computer is a dilution refrigerator, and when you open it, normally it's in vacuum and very cold. But when you open it, you can see what's actually going inside. It looks like a chandelier. It's actually called a chandelier. And it's gold-plated tubes and pipes and wires. And essentially, most of it is for cooling the chip down to 10 millikelvin. 10 millikelvin, okay, that's really, really cold. And we are cooling it. So most of it is the dilution refrigeration technology to cool the chip down. And then there's signaling going to the chip and signals coming out. So you will see that when you open the dilution refrigerator. So it looks aesthetically, it looks very, very pleasing, actually. And even some Hollywood movies have been made using a quantum computer as a villain, like to show that a quantum computer takes over the world and what it would do and that kind of stuff. So it looks very fascinating when you open it and take a look at it. But in real life, it's sitting in a vacuum. We cool the chip down. So right now, the 9 qubit chip, as I said, is just 6 millimeter by 6 millimeter. So the whole thing, the cylinder is roughly the size of your kitchen refrigerator. Okay, so it's not that huge. And then there's a control system stack, which is your standard server stack. So it's the size of a dining table, effectively, the whole quantum computer right now. Now, going forward, when we envision this 1 meter by 1 meter to fit in 500,000 qubits or 1,000,000 qubits, obviously the dilution refrigeration has to be a lot bigger than what it is. So at least the diameter has to be more than your size of the panel. So we are talking about roughly a diameter of 1.5 meters or maybe even 2 meters to fit in a 1 meter by 1 meter panel. So it's going to look a lot bigger cylinder than what it is today. But the control system stack should look comparable. I mean, that standard CPU, GPU stuff to drive it. So we don't expect that to change that much. So essentially, right now, it looks like a skinny cylinder. It will become a fatter cylinder. But everything else we think is going to be more or less the same.
You had mentioned superconducting qubits as being as a differentiating factor between Rigetti and your competitors. Let's talk about superconducting qubits. What do they offer in terms of advantages to other technologies like trapped ions or photonics?
So sure. So we believe superconducting is the leading modality primarily because of two factors. One, scaling. Because we are using semiconductor chip technology, we can take advantage of the 50 years of semiconductor industry know-how and can increase the qubit count, like the stuff we just talked about.
Yes.
We are leveraging the chiplet approach. We are increasing the density, the areal density, the way the classic semiconductor industry does. So we have all the benefits that semiconductor industry has learned over the last 5 decades. And that really helps us to scale up the qubit count. But probably the more important advantage we have in superconducting is speed. We are dealing with electrons, just like CPUs and GPUs are today. So we are relying on electron speeds. And so our gate speed effectively is in the tens of nanoseconds. Okay. When you go to other modalities like trapped ion and pure atoms, you are dealing with physically moving ions and atoms, which by definition are significantly larger than electrons. So the speed that they are at is like hundreds of microseconds. So when you say tens of nanoseconds to hundreds of microseconds, so basically we are 10,000 to 50,000 times faster in gate speed than a trapped ion or a pure atom type modality. And that creates a massive challenge for them when they are trying to do interfacing with CPU and GPU. I mean, the clock speeds are so different between a CPU, GPU, and a trapped ion or a pure atom modality that they have to create all kinds of buffers and stuff like that. We don't have that challenge. So that's why we can talk about hybrid computing, where we can coexist with CPU and GPU with superconducting QPUs. I believe trapped ion and pure atom type modalities will have a really tough time doing hybrid computing because of the speed differential. So two factors. Superconducting gives us a scaling advantage because of semiconductor industry leverage, but also more important one is the speed advantage. Having said that, the reason there are companies still investing in trapped ion and other modalities is because they have the fidelity advantage. We are dealing with engineered devices, so intrinsically we have more errors today than where trapped ion or pure atom type modalities are. So right now, our one qubit gate fidelity is fine. That's 99.9% already for most of us, IBM, Google, and so on. But our two qubit gate fidelity, which is where we entangle the qubits and see how accurately they entangle, collectively, the superconducting camp is between 99 to 99.5% right now. Whereas trapped ion, pure atoms, they are between 99.5 to 99.8%. So they are better in two qubit gate fidelity collectively than where we are. Now that gap is closing. We are already talking like 99 to 99.5 versus 99.5 to 99.8. 5 years ago, that gap was a lot wider, and it's already closed. Within 2 years, 3 years, I believe we will start overlapping with trapped ion and pure atom fidelities. All of us will obviously continue to improve our fidelities. So we will nudge all of our fidelities in superconducting camp to 99.6, 99.7. Google just recently published a paper. It's the first time I saw superconducting modality showing 99.7. Now it was a small system, but it's the first time I have seen 99.7% two qubit gate fidelity in the superconducting side. So I think we are beginning to catch up to trapped ion, pure atom, and other modalities in fidelity. But the benefits we have definitely are scaling and speed.
Very good. Let's talk about quantum cloud services. You've been using cloud services. Rigetti's been using cloud services to make quantum computing more accessible. What are some of the use cases, the key use cases, applications that you've seen from your user base, and how do you envision expanding this approach, this platform?
So good question. I mean, so we have offered our quantum computers on AWS and Azure, both, as well as our own cloud. We do see several thousand customers using our quantum computer routinely on those cloud service platforms. But the usage is not that high. So if you look at the actual usage of our 84 qubit quantum computer, even including both AWS, Azure, plus our own, we are still less than half utilized. So people are, and from what we can see, most of the users, they come from various different vertical markets: financials, education, defense. So the customer base is across the entire spectrum. What seems common is they are mostly research oriented customers. They are still primarily quantum physicists or algorithm developers who are trying to understand how to develop algorithms with a quantum computer. So they understand that these are what we call noisy era quantum computers. We call them NISQ, noisy intermediate scale quantum computing, NISQ. So they understand that. So no one's bringing production workload type applications and testing us compared to a GPU or something like that. And because they know that they will not look good when we do the comparisons. So most of it is research applications where they are fundamentally trying to understand how a quantum computer works, how they have to define their algorithms, and they are preparing for the future when we get better fidelity and qubit count.
Very good. And so let's talk a bit about, it's a related topic, but let's talk about the hybrid quantum classical systems. I know that Rigetti has been a pioneer in this area. It makes a whole lot of sense. I'd like to explain for the audience here, how do you see these systems unlocking near-term value for industries before we achieve fault-tolerant quantum?
Yeah. So, I mean, our vision clearly is that hybrid quantum computing is going to happen before full-fledged fault-tolerant quantum computing.
Agreed.
We are in the noisy era right now. We are still dealing with fidelity issues and stuff like that. But there are some applications where quantum computing can do a better job than what a CPU or GPU can, specifically applications that are probabilistic in nature. So when you're asking questions like, what are the chances of something happening? What are the chances of an economic recession? A question like Moody's would ask. What are the chances that a particular transaction is fraudulent, like big bank would ask? What are the chances that the weather is going to do this? Meteorological kind of applications. Or what are the chances that a protein would fold this way or that way. Those would be pharmaceutical type of applications. So almost any probabilistic type application, fundamentally quantum computing seems more suitable than classical computing because of the way our qubits work, they entangle. I say that it's more like a human brain, the way our quantum computer works. So just think of how our human brain works with a bunch of neurons that are entangled, and we get analog input, a few neurons act on it, and we get analog output. Quantum computer is very similar to what a human brain is doing. So things that are probabilistic become very difficult for deterministic things like CPU and GPU. So that's where when you look at the algorithms that you have to do with CPU and GPU for these probabilistic applications, they become increasingly complex and very, very intensive. Whereas with for quantum computers, with our qubits and simultaneously be able to tackle the problem, those problems become valuable. So our view is that a QPU, quantum processing unit, will start coexisting with a CPU and GPU in data centers. And some of the probabilistic type applications will move over to QPU. The standard computational stuff will continue with CPU. The standard parallel stuff will continue with GPU. That's the way we believe the ecosystem will evolve, even while we are still dealing with noisy era quantum computing. So we are talking roughly 3 to 5 years from now. Okay, that's what our vision is, that this coexistence will happen in data centers. Long term, once we reach this fault tolerant quantum computing, there's the VC that quantum computers could be standalone systems that are taking the full workload, production workload in a data center. But even then, we never think that a fault tolerant quantum computer will be sitting in an isolation and there will not be a CPU or GPU in the vicinity. So just like if you look at how the data center has evolved in the last 20 years, I mean, 20 years ago, it was all CPU. Now it's CPU and GPU. Obviously, GPUs, the volume of GPUs is still small. It's just that the value of GPU is much higher. We think QPUs will be similar. Volume will be smaller than CPU and GPU, but the value would be much higher. That's our view of how the coexistence will evolve over the next decade.
How long until we have those fuller, not quite standalone, but essentially standalone quantum computers?
How long before that happens? Is that the question?
Yes, timeline.
We think it's at least 7-8 years from now, where a fault-tolerant quantum computer with 500,000 qubits that will sit alone. We are dealing with that. And as I said, even with that timeline, our view is it will always be still in coexistence with some CPU and GPU.
We had talked a bit about accessing quantum computing power today in practical terms, limited users, but still in practical terms, in a cloud context, and also how these hybrid classical systems can facilitate usage and commercialization today, or at least practical solutions today. You had mentioned some of the areas, the obvious areas, defense and education, where you see your users starting to show up. Can you give us a specific example of a problem that somebody has come to solve, or at least the type of problem that somebody would come to solve? Like, what are they asking your quantum computer today to do or to solve? What problem to solve?
Sure. So one example I can pick, and we have published a few papers in this area, is with Moody's. Moody's is obviously a big financial organization, and central banks of the world are asking Moody's all the time, what is the likelihood of an economic recession happening? Because that's such an important input for determining the interest rates and stuff like that. And that's what Moody's does for last 100 years. They have a lot of data, classical data with classical algorithms, and they're trying to predict economic recession. And the best they can do right now with all of their prior history is about 77%. So they can predict economic recession accurately only 77%. That means 23% of the times they're wrong, which is a huge problem, obviously. So we have been working with them for 2 or 3 years now, and we showed them that you can take their data, their classical algorithms, you're just mapping their data with a quantum computer and feeding it back to their algorithms. And we can improve even as simple as a 9-qubit quantum computer. With a simulator, you can improve the number from 77% to 86%. Okay, wow. That's huge.
Yes,
and obviously, that's just a 9-qubit one. And then we are doing both simulation and actual work. The actual is at a little lower because simulation is perfect by definition. So the actual is at 83%. But still, 77 goes to 86 with simulation, and the current noisy era quantum computer is at 83. So our job as a quantum computing development company is to close that gap between 83 and 86. But the bigger challenge for us and Moody's is when we get 100 qubit and 1000 qubit quantum computers with high fidelities, can we truly bump up that number 86% to 95 or 99%? That would be a huge application. I mean, if we can go back to the federal banks of the world, right, the central banks of the world, and say we have improved prediction of economic recession, that, I mean, you realize what kind of value is associated with those decisions. So that's just one. Then obviously the whole pharmaceutical area is an obvious one, right? I mean, there are millions and millions of variants of drug molecules because of the multiple proteins and how they fold and unfold. And right now, all that work is done on classical computing. And practically what they do is that they believe that they narrow the number of potential molecules down to 100 or so, because that's all they can experiment with. And so they are really taking some guesses as to which direction to go. With a quantum computer, you don't need to potentially worry about narrowing the number down to 100. You can let the simulations run and let it run for thousands, if not millions of variants, and say, this is the variant that I think has the most likely chance of success. So there are many practical applications where we see classical computing already struggling, where quantum computing is showing potential to improve. We are not quite there yet. I'm not ready to say declare victory and say we can predict economic recession better than what Moody's can with classical, but we need to continue to work on in these kinds of areas. But I see a lot of potential in these areas.
Very, very promising. Let's talk about Forest. Rigetti has contributed substantially to quantum computing programming tools like Forest, an open source tool. How have these tools helped shape the broader quantum development community, and what advancements can we expect to tools like this in the future? And also, I think more to the point from a commercial standpoint, how does the development of this open source project serve Rigetti's shareholders?
All good questions. I mean, fundamentally, we believe we are in the R&D mode right now. We are still very much developing technology. When you are developing technology, you owe it to the community at large that you share some of your thoughts and ideas. We all understand we are in a capitalistic system. We all want to survive and make money for our shareholders and all that good stuff. It's all there. But when you are in R&D, first you have to worry about growing the pie before worrying about what part of pie you are going to get. Right now, the pie by definition is zero because we are still in R&D mode. So it's the onus is on us and other companies like IBM and Google to share things so that we can collectively grow quantum computing community. Once we start growing, then we can fight and compete with each other. But right now, we are still in the early stages. So we are doing our part with things like Forest. IBM is doing its part with things like Qiskit and so on. And we all share information in conferences and proper venues. There are things we could legitimately learn from each other. And we try to do that to help the community at large. So yeah, sometimes it becomes contradictory. I mean, sometimes shareholders have a right to challenge us and say, why are we sharing these things? But I think my answer is, if the size of the business is 5 years from now, who's going to win that business? Or does it matter? So let's make sure that there is a viable multi-$100 billion business 10 years from now, and do our part to enable that. And then we'll try to go a big chunk of that.
I want to end with a somewhat personal question, I'll confess. You had mentioned the word simulation, and I am a big nerdy simulation theory guy. And so I'd like to ask you, are we living in a simulation?
This question keeps coming up. I mean, there are some really freaky things that go on with quantum computing that start overlapping with human brain and stuff like that. And you start wondering where we are headed here and where we have come from. And sometimes you do become philosophical about what is our role going on right now. And is it really, are we part of some kind of a gigantic simulation or not? But then they get so complex, I finally come back to reality and say, let's just focus on the next year and now, and not ask too many difficult questions that become philosophical in nature.
Very good. Subodh, it was an absolute pleasure speaking with you. Thanks for taking the time. Very exciting work at Rigetti, and very excited to see where Rigetti goes and where this quantum conversation takes us. Thank you very much for the time.
Well, thank you for your interest. Look forward to hearing from you.